By solving the Schrodinger equation for hydrogen atom, we obtained the wave functions which we called orbitals and the corresponding energies. The energies corresponded to the orbitals and we called them orbital energies. When we looked at the energies of hydrogen atom, which was essentially a single electronic species, we saw one pattern of energy level, the ordering of energy level. When we saw the multi-electronic systems, we saw a different pattern of the ordering of energy levels. We saw that for multi-electronic systems, we could arrange the orbitals according to their n plus L, which reflected the increasing order of their energy. This is now what I am showing here is the orbitals ordered according to their increasing value of n plus L, which also reflects their increasing energy. There are a few features that you can see here. You can see that for any value of orbital angular momentum, let us say we are considering s orbital. For any value of orbital quantum number, when you see the different orbitals of corresponding to different principal quantum number, so 1s, 2s, 3s, 4s or 2p, 3p, 4p or 3d, 4d, 5d or so on and so forth, you see that for a given orbital quantum number, as we increase the principal quantum number, the energy of that orbital is increasing. Energy of 4s is greater than energy of 3s is greater than energy of 2s and 1s is anyway the ground state. This is one observation. The other observation is that if you fix a particular value of n, the principal quantum number, let us say 3, then it has got for n equals 3, we have got 3s, 3p and 3d. You see that for a given value of principal quantum number, as you increase the orbital quantum number s to p to d, the energy is increasing, and this trend you actually see in all other principal quantum numbers 4s, 4p, 4d, 4f and so on and so forth. So, there are many interesting things that are happening in a multi-electronic system, and this is what we are try to understand. In a multi-electronic system, of course, we know that we have a nucleus. Let us say that this nucleus has z number of protons. So, it has got z times E, the charge of the nucleus. Now, this is the nucleus and we know we have several electrons and they are going around the nucleus. Of course, this is after discussing quantum mechanical treatment, this picture may not be the most accurate picture, but this is a simple picture which will drive the point. So, now what I have done is that let us say I have these 3 different electrons at 3 different orbitals, right. We saw, if you remember, the orbital energy of the energies of all the orbitals were coming out to be negative, and from there we concluded that the negative value indicates that the electron is stable in the atom. So, the electron is happy to be in the atom. Where does this electron get stability from? One source of stability is the interaction between electron with nucleus. Electron is negatively charged, nucleus is positively charged. So, the opposite charges they will attract each other and that gives an attractive interaction energy. That is true for all the electrons, right. You will immediately appreciate the fact that which electron will have better interaction with the nucleus. The answer is that electron which is closer to the nucleus. So, in this case electron 1 being closer to the nucleus will have better attractive interaction energy compared to electron number 3. So, this kind of explains that why the orbital energy increases as we go away from the nucleus, as the electron stays away from the nucleus. It is not only that, there are other features. This is what we will discuss now. You imagine that each electron is under the attractive influence of the nucleus. At the same time, each electron is also facing the electron repulsion energy which is coming from other electron. So, consider the electron number 2. it has got negative charge, electron number 3 also has negative charge. Now, these like charges, negative charge of electron 2 and negative charge of electron 3, they repel each other. So, electron number 2 for example, not only has an attractive interaction with the nucleus, at the same time it is also being repelled by all other electrons of the atom, and this is the case for all the electrons in this atom. Now, the other thing you would notice is that so since each electron is under the influence of an attractive interaction and a repulsive interaction, that electron will be more stable for whom the attractive interaction is much stronger than the repulsive interaction coming from other electrons. And when is that going to be? That is going to be for the electron number 1. This is because it is much closer to the nucleus. Now, electron number 1, by the virtue of being close to the nucleus, does another thing. What it does is that it screens or it shields the nucleus, or we call that it screens the nucleus from interacting with the electron which are farther from the nucleus. Similarly, electron number 2, which is now closer to the nucleus compared to electron number 3, by interacting with the nucleus, it actually screens the nucleus from interacting sufficiently strongly with the electron number 3. So, in a sense, each electron screens the nucleus from interacting with the electrons which are farther from the nucleus than that particular electron is. So, we see that is in other words, the electron number 1 looks at the nucleus and finds the full glory of this nucleus. That means, it looks at all the protons or entire positive charge, that is Z. But when you come to electron number 2, you see that electron number 2 does not actually see the full glory of the nucleus, because electron number 1 kind of screens the nucleus from interacting with electron number 2. So, electron number 2 will feel as if there is not Z charge on the nucleus, rather Z minus a small number. We do not know what this number is, but A is a small quantity compared to Z. Similarly, electron number 3 will not see the full nuclear charge Z, rather it will see Z minus B, which is where B is another small quantity. In general, we can generalize that any electron actually does not see this value of Z nuclear charge, rather it sees what we call as Z effective, which is given as Z minus, let us call sigma. This sigma is known as screening constant. The sigma tells that how much this particular electron is screened from the nucleus, and that particular electron sees the nuclear charge not as Z, rather Z effective, which is less than Z. So, you can see as n increases, the principal quantum number increases, sigma increases, and then the Z effective becomes smaller and smaller compared to Z. So, in a sense, we can write down, if we compare 1s orbital, 2s orbital and 3s orbital and compare their sigma values, we will see for sigma or the screening constant, we see this trend, where for 3s screening factor, screening constant is much larger compared to 2s, and in turn which is again larger than 1s. In other words, we can also write for Z effective. In that sense, we see 1s has greater Z effective than 2s compared to 3s. What does that mean? That 1s electron, when the electron is in 1s orbital, it sees the full nuclear charge Z. When it is in 2s orbital, it does not see the full nuclear charge, rather it sees Z minus sigma, and 3s orbital it sees Z minus sigma, but please remember that sigma for 3s orbital is different from sigma of 2s orbital. This kind of explains that why we, as we go higher and higher principal quantum number, the energy of the orbital increases. Now, next we will discuss about the fact that we observed that for a given principal quantum number n, we see that the orbital energy increases as you go higher and higher in orbital quantum number. So, 3p has greater energy than 3s orbital, and 3d orbital has energy greater than 3p orbital. We will try to understand this next. If you remember, this is the probability distribution of electron for, this was for 1s orbital, this is for 2s orbital, and this is for 3s orbital. You saw that 1s orbital we have this single density. For 2s orbital we see that probability density is somewhere here, and then there appears a node, and then electrons are also have probability to be found farther from the nucleus, and then 3s had this feature. We also discussed the probability distribution plot like this. In this plot, if you remember, we discussed that this is the probability distribution of 1s orbital. This was the probability distribution of 2s orbital. There are two peaks. The first, the small peak, is coming because of this electron density. The second peak here comes because of the electron density that is seen in this region. Similarly, this is for 3s. So, this is for 3s, this is for 2s, this is for 1s. For 3s, you see three different peaks. One, probability density at a smaller value of r, the x axis is r, which is the distance between the electron and nucleus. So, at a smaller value of r, and then you see another density corresponding to this distribution, and then the final density corresponds to this distribution. This is what we saw for 1s, 2s and 3s. What we see here, if you observe, let us say for 2s orbital, the electron in 2s orbital kind of penetrates into the 1s region. This is the 1s orbital region. In the 2s orbital, the electron kind of penetrates into the 1s shell, which is shown by this density. And similarly, 3s electron penetrates into 2s shell and 1s shell. If I compare the probability distribution for 2s with 2p, this is for the 2p orbital, you would see that 2p does not have this penetrating capability. So, the probability distribution in 2p is farther from the nucleus comparing as compared to the electron in the 2s orbital. So, in a sense, if the electron is in 2s orbital, it can penetrate closer and closer to the nucleus, but when it is in 2p, it cannot do so. When you compare 3s, 3p and 3d, we again see the same feature. The electron which is in 3s orbital can penetrate into 2s shell and 1s shell. So, it can come closer and closer to the nucleus. Compare that with 3p, 3p does a worse job than 3s. It can penetrate, but only to the second shell. This is the shell for the 2p. But in case of 3d, it cannot penetrate closer to the nucleus. So, in this way we see that as the orbital quantum number increases from s to p to d, we see that the electron can penetrate as the for lower orbital angular moment, orbital quantum number when s is 0, the electron can penetrate much effectively closer to the nucleus. So, therefore, the 2s electron, the electron in 2s orbital will be much more stable than 2p, and therefore, the same reason applies for 3s orbital electron, which is much close, can go closer to the nucleus, has less energy compared to 3p, and 3d electron has even higher energy. So, if I compare the screening constant for 3s, 3p and 3d, I can write this. And if I compare the z effective, I will say, so the larger the z effective, this more stable the electron is. So, this gave us an idea about why we see the trend that we see in the orbit, the energy ordering of the orbitals. Next, we are actually now well equipped to discuss about the electronic structure in more general terms. We will now are in a position where we can take any atom. By that atom I know how many electrons, how many protons are there, and we can discuss about how the electrons are arranged in that atom. So, this is what we are going to do next. We are going to start discussing about filling electrons in orbitals. While discussing this, our first point of discussion is what is known as Pauli's exclusion principle. It is a very important principle that plays a fundamental role in electronic structure of atom. What does Pauli's exclusion principle say? That no two electrons in a given atom, in an atom, can have the same set of quantum numbers. We have actually discussed 4 quantum numbers. The Pauli's exclusion principle says that no two electron in an atom can have the same set of 4 quantum numbers. What are these 4 quantum numbers? N, L, M and ms. The principal quantum number, azimuthal quantum number, the magnetic quantum number and the spin quantum number. We know what these quantum numbers represent. So, looking at this, let us consider one s orbital. Right. For one s orbital, n is 1, L is 0, and since L is 0, the possible value of m is again 0, because there is only one orientation for s orbital. And what are the values of ms? We know ms can have either plus half or it can have minus half. So, in this way, the 1s orbital has a given value of n, given value of L, given value of m, we cannot play with it. All we have is this, there are 2 possible values of a spin quantum number, either it can be plus half or it can be minus half. And therefore, Pauli's exclusion principle says that you can have the outcome of or the consequence of the Pauli's exclusion principle is that an orbital can have maximum 2 electrons, not more than 2 electrons. Why? Because if I have already 2 electrons, one of them will have plus half spin, the other one will have minus half spin, because they cannot have the same set. And if I introduce another electron, the third electron can either take plus half spin or take minus half spin. And if it takes plus half spin, then again it violates Pauli's exclusion principle, which says that 2 electrons cannot have all the quantum numbers same. So, essential outcome of Pauli's exclusion principle is that an orbital can have up to 2 electrons, and the second outcome is that these 2 electrons in a given orbital, they will have opposite spin. In an orbital diagram, if I write 1s, so I have one up spin electron and then I write another down spin electron. So, one orbital can maximum contain 2 electrons and they have to be of opposite spin. This is the consequence of Pauli's exclusion principle. This we will keep in mind and look at other rules that are useful to describe filling of electrons in orbitals. The next principle that we are going to discuss is what is called as building up principle. This also goes by a German word which is Aufbau, which means building up or construction, Aufbau principle. It essentially says that the rule that will be used to construct or to build up the electronic arrangement. what does this Aufbau principle says? It says that the orbitals are filled in the order of their increasing energy. The energy is the determining factor that decides which orbitals will have to be filled first and which orbitals can be filled afterwards. So, we already know how the orbital ordering looks like. So, this follows this n plus L pattern, and this is the ordering. So, building up principle or the Aufbau principle tells that you must fill first the orbital of lower energy before you start filling the orbital of higher energy. We will take a few examples. Let us start from the beginning. We have hydrogen, which has one electron. So, the lowest energy orbital is 1s. So, I give one electron to 1s, it is happy. Let us take the next one, which is helium. It has got 2 electrons, and I have the first orbital, I see 1s, and I know from Pauli's exclusion principle that it can hold 2 electrons. So, I gave both the electrons to helium, and I can orbital diagram I can write in this way, one is up spin, another is down spin. The next one is lithium, which has got 3 electrons. So, I see 1s, I cannot give all 3 electrons to 1s orbital, because that will be violation of Pauli's exclusion principle. So, 1s and it is full. Now, I have to go to the next orbital. Who is the next orbital? 2s, and 2s, how many electrons can it hold? It can hold 2 electrons. So, I gave 1 to this 2s orbital. The orbital diagram looks like this. In this way, I can go on building higher and higher Z values. Let us take one more example, that is of sodium, which has 11 electrons. So, I will start from 1s, it can hold 2 electrons. Then I am left with 9 electrons, because 2 electrons are filled. I have 9 more electrons. So, then I go to 2s orbital. Then I see 2s orbital can take 2. So, I gave it 2. So, I am done with 4 electrons. I still have 7 electrons to take care. Then the next orbital in sequence is 2p, and if you remember, 2p actually has 2px, 2py, 2pz. So, there are 3 compartments. So, let me keep building this orbital diagram. So, 2 in 1s, 2 in 2s, and 2p has 3 compartments. This is for px, py, pz, actually ordering does not matter. So, they are all equivalent. So, I have got 11 electrons, 4 are gone. So, I have 7 left. So, I am giving all 6. So, 2p 6, and then I am left with 1. So, I can give the the last electron to the next orbital, which is 3s. In this way, I can go on building. If you notice, let us look at our periodic table. The periodic table. So, this is 1s the hydrogen atom, helium atom, and so on, and I will keep the orbital ordering pattern here, and we will try to understand how to fill the any element of in this periodic table. So, I start with this. I have first element, which is hydrogen. It has got 1s, 1 electron. So, I fill 1s orbital here, and if I come to helium, I can give 2 electrons to this 1s orbital. So, hydrogen and helium are gone, and then when I start from lithium, I have to start filling 2s orbital. So, 2s gets filled starting from lithium. So, 2s is taken care, and lithium and beryllium, by lithium and beryllium I finish my 2s orbitals capacity, because it has got only 2 electrons, it can take only 2 electrons, and when I come from boron, I would have to start filling 2p orbital, because 4 electrons are taken care, and the 5th electron will start occupying 2p, and since 2p can hold 6 electrons, next 6 elements boron, carbon until neon, they will be filled within the 2p orbitals. When I start coming to sodium, which has 11, you already saw that I have to start filling 3s, and when I finish magnesium, 3s is finished. Then starting from aluminum to argon, so in this case I filled 2p, and for aluminum I am filling 3p. This color is not visible, so let me use another. So starting from boron, I started filling 2p orbitals, starting from aluminum I started filling 3p orbitals, and similarly for starting from potassium and calcium, so 3p is gone, so I have 4s, so I can start from 4s. After 4s comes 3d, so potassium and calcium 4s capacity is done, and the next orbital is 3d. So starting from scandium, which has 21 electron, I will start filling 3d, and you know 3d has 5 magnetic quantum numbers, possible quantum numbers. So therefore 5 different orbitals, and it can hold up to 10 electrons, each orbital can hold 2 electrons. So starting from scandium to zinc, the next 10 elements will be filled in the 3d orbitals. So starting from here I am filling in 3d orbital, and starting from gallium the next orbital is 4p. So you can see that as I come to the next row of the periodic table, I am starting to fill higher and higher s orbitals, and the p orbitals are getting to filled with from boron, aluminum, gallium, indium, thallium, and the d orbitals will start getting filled along this direction from here. So this is how we also name them as s block elements, p block elements, d block elements. These are all the outcome of electron filling pattern. So you can take your periodic table and can write down the electronic configuration of any atom that you wish. Now we will take 2 more special cases. That case is, let us discuss about carbon. Carbon has got 6 electron. It has got 1. I'll give 2 electrons to 1s, then 2 more electron to 2s, and then I am left with 2 electron. I will give that to 2p. If orbital diagram I will write this way, to 1s 2, and 2p has 3 different compartments, and I have got 2 electrons to give. How can I give it? I can, the way I have been doing, I can perhaps do this way, or is there another possibility? I think so. I can do this. Is there another possibility? Yes, I can do this. See, there are other possibilities, like instead of filling this compartment I can fill this compartment, but that is not really a unique possibility, because all the compartments are essentially equivalent. So that they are not, they will not give you new possibilities. So these are the 3 possibilities that I have to fill this 2p electrons in 2p electrons in the for the carbon atom, but which of them is the correct one? The answer to that question comes from Hund's rule of maximum spin multiplicity. What does it tell? It tells that when more than one orbital has same energy, then electrons are filled in the separate orbitals, and they carry parallel spin. This is what Hund's rule tells. So it says that if there are more than one orbital which have same energy, for example, in this case 2px, 2py, 2pz, there are 3 different orbitals and they have got all same energy. So, we must fill electrons in the separate orbitals and we must give them parallel spins. So, for example, this configuration what we have done is wrong. Why? Because it is in violation of Horn's rule, which says that the electrons have to be filled in separate orbitals. So, I filled the electron in both the electrons I gave to the same orbital, that is wrong. In this way, in this the second case I have done correctly, because I have given electron to the 2 different orbitals, and in the third case also I have done correctly, because I have given them in separate orbitals. But in the third case I made another mistake, and that mistake is that they do not carry parallel spin, they carry opposite spin. So, this is again violation of Horn's rule. So, of the 3 possibility, this one is the correct one. So, the way we fill the electron is that we first fill each orbital singly, and once all orbitals are filled, then we will start filling the we will start giving second electron to an orbital, and when we give the second electron we must give it with the opposite spin, because that is dictated by Pauli's exclusion principle. Otherwise, 2 electrons cannot have the same spin in the same orbital. So, together taking together Horn's rule and Pauli's exclusion principle, we can give we can write down this electronic configuration of this carbon atom. What you see here has important consequences. The thing is that why is this configuration accepted and not these 2? The answer to that is that this configuration has lower energy. This configuration is more stable, and its stability comes from what is called as exchange interaction energy or exchange correlation energy. We call that as just exchange energy. What do I mean by this exchange energy? You see, when the 2 electrons are in this way, so each of these 3 components are compartments are equivalent, and now if I keep the 2 electrons parallel spin, actually what I do is that I have more possibility to exchange or interchange the electron in these compartments, and if by keeping them parallel I invoke the indistinguishability of the electron, and that gives me additional stabilization. In the opposite case, since the 2 electrons can be now distinguished, one has up spin, another has down spin, so that indistinguishability does not come into play. So, that stability which is coming from indistinguishability of the electrons is gone in the third case. So, this way we get most stable configuration because of this region, because of the exchange energy. Now, we can take this argument further. I will try to fill the electron in nitrogen. Nitrogen has 7. So, 1s2, 2s2 and 2p3. I have got 2 electrons here, 2 electrons here, and I will fill like this. I will first fill. You see, in case of nitrogen, when there are 3 electrons, I will have maximum exchange energy. This will be a very stable configuration. Why? Because each of the compartment has single electron. So, now I have got 3 electrons to exchange with, and they are all indistinguishable. So, therefore, exchange energy is more favorable. Similarly, if I have a situation where I have a d orbital has 5 compartments. If I have a situation where there are 5 electrons in d orbital, so this is p3 configuration. If there are 5 electrons in d orbitals, which is called, let us call d5 configuration, this will also be very stable because of this exchange energy. Similarly, if I have f orbital which has 7, 1, 2, 3, 4, 5, 6, 7, F7, this is also very stable configuration. So, we see when you have P3 or D5 or F7, these are called half filled shells. The half filled shells provide very stable configuration. Similarly, the full filled shells also give good stability. So, full filled and half filled shells are very important for stability. We will now take up 2 more examples. The first example is chromium. We have got 24 electrons in chromium. So, for chromium I can write down as 1s2, 2s2, 2p6, 3s2, 3p6. If you see chromium, this appears here in this place. Before chromium, you see that argon has 1s2, 2s2, 3s2 and 3p6. If you check this configuration 1s2, 2s2, 3s, 2p6, 3s2, 3p6, I have got 18 electrons here and this is the configuration of argon. So, instead of writing all these things, I can write simply argon and then follow what is coming. So, after 3p, I will have to fill the 4s electrons and then comes 3d electrons. So, I have 4s2 and by 4s2 I am done with 20 electrons and I am left with 4 electrons. So, I gave 4 electrons. So, this I can equivalently write in simple way as 4s2 3d 4. These represent core electrons and these are called valence electrons. The valence electrons are useful for doing chemical reaction, that they have the reactivity. The core electrons are more or less inert. So, this is the configuration that I am getting. But look at this situation, if I draw the orbital diagram. So, this is 4s and this is 3d. I have 4 electrons. So, I am filling them up. I see that this is just one less than D5 situation, but I know that D5 situation is very stable. This is exactly what happens. Chromium finds a more stable configuration, which is this. What it does is that it transfers one electron from 4s to 3d. By that, what it gains is that a lot of exchange energy, and that therefore, this configuration is more stable and this configuration is less stable. So, when chromium we see chromium in this configuration. We can take another example. In addition to chromium, there is another element copper, which has got 29 electron. I can again write the core and valence configuration, 18 electrons are taken care. So, I have got now 11 electrons to fill. I give 2 electrons to 4s and next is 3d and I am left with 9 electrons. So, I gave them. If I draw the orbitals 1, 2, 3, 4, 5, I have 6, 7, 8, 9. Now, what we see here is that only one orbital is half filled, the remaining are full filled. So, we know that both half filled and full filled shells are stable. So, in this case there is a change in the configuration, copper adopts a change in the electronic configuration and goes to 4s1 3d 10. And in this case all the 3d orbitals are doubly occupied, and this is the stable configuration of copper. Another example where this factor plays out is gadolinium, which has 64 electron, and I would suggest that you please do this yourself. You see that you start with xenon, which has already 54 electrons and you will be left with 10 electrons. You would first write down the you will first fill the electrons according to the orbital energy, and then you should try to figure out if there is a possibility of another stable configuration, the way we saw in chromium and in copper, and find out write the correct configuration of gadolinium atom. In this series of lectures, we have travelled a long way. We discussed the discovery of various subatomic particles, the discovery of electron, proton, neutron. We saw how nucleus was discovered. On the basis of those discoveries, we went through different models of atom, starting from Dalton's atomic model, which was very rudimentary in nature. Slight improvement was given by plum pudding model of J.J. Thomson. We talked about Rutherford's model, and finally we came to Bohr's model. Bohr's model was quite good for hydrogen atom or other single electronic species, but it was off the mark for multi-electronic systems. Then we had to take shelter to a different theory, which was quantum theory. The quantum theory was in the picture because of several developments. For example, there were photoelectric effects and black body radiations, which could not be explained by the old theory, the classical theory. And during those course of scientific discoveries, we learned that light is both a wave and a particle, followed by the hypothesis of de Broglie, who suggested that matter also behaves like a wave. Then there was Heisenberg's uncertainty principle, which said that for microscopic objects you cannot simultaneously determine their position and momentum. With these new principles, with these new fundamental rules, the quantum mechanical model was formulated, and we did that for an atom, and in principle we can extend the quantum mechanical model to any larger molecular system. We solved the quantum mechanical model in terms of the Schrodinger equation, and the solution of the Schrodinger equation gave us the orbitals and their energies. We also saw that the orbitals had different shape, different orientation, and they could be described by what we call quantum numbers, the principal, azimuthal, magnetic and spin quantum numbers. And we also discussed about how electron-electron correlation affects energy ordering of these orbitals. At the end, starting from Dalton's pure crude atomic theory, we came to a situation where we could discuss the electronic structure of a multi-electronic atom. We could take any atom from the periodic table and discuss how the electrons are arranged in that particular atom. Next, what we will do is we will go through the previous year JEE question papers, and I have done that for you. I have gone through the last few years JEE question papers and selected questions that were from the topics that we discussed. We will go through a few questions and we will see how to solve them. The first question is given here. The question says that there is this hydrogen like species lithium 2 plus, which is in a spherically symmetric state S1, and this state has one radial node. Upon observing light, this ion lithium 2 plus ion undergoes a transition to a state S2. So, it was in S1 and it goes to S2 state. The state S2 has one radial node. S1 had one radial node and S2 also has one radial node, and the energy of state 2 is equal to the ground state energy of the hydrogen atom. This is the information that we have. The question asks, what is the state S1? What do we know about the state S1? We know that it is a symmetric state. By symmetric, what do we mean? We know that only s orbital is symmetric, sorry, it is a spherically symmetric, s orbital is spherically symmetric. So, S1 state must be one s orbital, and then it says that it has got one radial node. Among s orbital we can have 1s, 2s, 3s, 4s, we do not know which one, but it also says that it has got only one radial node. We know 1s orbital has no radial nodes, 2s has got one radial node, 3s has got two radial nodes, and so on and so forth. So, from these two information we know that this state state S1 is 2s orbital. All right, this we answer. The next question tells that the energy of the state S1 in units of the hydrogen atom ground state energy. So, we have, what do we know about the energy of the lithium 2 plus? We know that its energy is minus 13.6, this comes from the Bohr's atomic model, z square divided by n square, and the energy is in the units of electron volt. So, we know this is the energy of this lithium 2 plus. What it says that state S1 has the same, it wants us to find out the energy of state S1 with respect to the energy of ground state hydrogen atom energy. So, let us find out the energy of state S1. So, minus 13.6, Z is 3 because it is lithium. So, 3 square is 9, N is 2 because we have already found out that it is in 2s orbital. So, this is 9 by 4 electron volt. And what it asks? It asks in the units of the hydrogen atom ground state energy. What is hydrogen atom's ground state energy? We can find that from this equation itself. For hydrogen atom Z is 1 and ground state N is 1. So, this term does not give any contribution. So, we have only hydrogen atom's ground state energy is minus 13.6 electron volt. So, in the units of hydrogen atom's ground state energy, this is 9 by 4 and which is 2.25. This is the answer. The third question tells that the orbital angular momentum quantum number of the state S2 is what? So, it wants us to find out S2 state, what is its identity, and find out its orbital angular momentum quantum number. The S2, what do I know about S2? S2 has one radial node, that is one piece of information. The other is its energy is equal to the ground state energy. If I want to find out the energy of S2, let me write down this energy is again Z square by N square in the units of electron volt. Z is 3 for lithium 2 plus. So, this quantity is 9 and this energy for S2 is equivalent to the energy of hydrogen atom ground state, and what is that? That is 13.6. When will this quantity be equivalent to 13.6? It will be when Z square divided by N square is 1, or in other words N is equivalent to Z. So, this way we got to know that principal quantum number of S2 state is equivalent to the atomic number of lithium, which is N is 3. So, now we know it is N is 3. So, if it is 3, then it can be 3s or 3p or 3d. What more do we know? The question tells, it says that it has got one radial node. So, we can find out how many radial nodes we have in case of 3s, 3p and 3d. We know that 3s has got 2 radial node, 3p has got 1 radial node, 3d has no radial nodes. So, the final answer is that the state S2 is 3p, and since it is 3p, its orbital angular momentum quantum number is 1, which is this answer. We will take up the next question. It says, the next question tells that the maximum number of electrons that can have principal quantum number n equals 3 and spin quantum number ms equals half. So, n is 3. If n is 3, what are the orbitals possible? 3s, 3p, 3d. In 3p, I have 3px, 3py, 3pz, and 3d, I have 5 different orbitals, 3d xy, yz, zx, x square minus y square and z square. I am not writing them down. And it also says that find out the electrons that have spin quantum number minus half. I know each orbital, for example, 3s orbital can have 2 electrons and one of them will have plus half spin, the other one will have minus half spin. Similarly, for 3px, 3py, 3pz, and each of the 5 3d orbitals will have one electron with ms plus half, the other electron with ms minus half. So, that means I will have one electron from each orbital that will have ms minus half. So, the answer to this question is essentially counting the number of orbitals 1, 2, 3, 4, 5, 6, 7, 8, 9. So, 1 plus 3 plus 5. So, there are 9 orbitals for n equals 3, and each orbital can have only one electron with ms equals minus half. So, the maximum number of electrons that can have these two quantum numbers are 9. The next question is along the similar line. It says that in an atom, the total number of electrons having quantum number n equals 4. So, it says 4, n is 4. It also says ml, the mod of ml is 1. What we called m during our discussion is called as ml, because we have ml and ms. ml is the magnetic quantum number that we know, and ms is the spin quantum number. So, ms is minus half, mod of ml is plus 1. When n is 4, I can have L as 0 or 1 or 2 or 3. When L is 0, the values of m or ml is only 1, that is 0. When L is 1, values of ml is -1 or 0 or +1, because I know that -L to +L. When when L is 2, I can have m value -2 or -1, 0, +1, +2, and similarly -3, -2, -1, 0, 1, 2, 3 when L is 3. Now, the second part of the question says the mod of ml should be 1. When is that possible? So, that means ml can be either be -1 or +1. So, let us find out the orbitals that satisfy this. So, how many did we find? We found 6 different orbitals. So, this corresponds to px, these 3 are px, py, pz, and we know each of px or py can hold maximum up to 2 electrons. So, the next requirement is that the electron should have -12 spin, and we know from the discussion of the last question, each orbital will have 1 electron with +12 spin and 1 electron with -12 spin. So, if we want the electron with -12 spin, so I will find 1 electron in each of these circled orbital which satisfy this. So, how many are there? 2 plus 2 plus 2, which is 6. We will look at the next question. It says that not considering the electronic spin, all right, the degeneracy of the second excited state, which is n equals 3, of hydrogen atom is 9. Do we know that? If you remember, for hydrogen atom, the orbital energy depended only on the value of principal quantum number n. So, the lowest energy or the ground state was 1s, the next state was 2s and 2p combined, this is 2s, 2p, they had the same energy because they had the same principal quantum number. The third energy level 3s, 3p, 3d, this is the ground state, this is the first excited state, this is the second excited state. Second excited state has n equals 3, that you can see here. How many orbitals were there? 1, 2, 3, 4 plus 5. So, there were 9. So, this question we understood this part of the question. The question actually asks, if this is the case, what is the degeneracy of the second excited state of H minus ion? Now, H, this is for H, which has 1 electron, H minus has got 2 electrons, right, and this is a multi-electronic species. If for multi-electronic species, we know that the ordering depends on n plus L. So, we will write down that 1s, then 2s, then comes 2p, then comes 3s, and so on and so forth. What is the ground state in H minus? This is the ground state. This is the first excited state, and this is the second excited state. And the second excited state is essentially 2p. And how many orbitals are there in this case? The degeneracy is 3. The final answer is 3. The degeneracy of the second excited state of H minus is 3. The next question is from photoelectric effect. It says that the work function of some metals, it is listed below. So, lithium, sodium, potassium and others. Their work function, if you remember, work function indicates that the minimum amount of energy that you must supply to the metal before you can take out its electron from it, from the metal. So, this essentially indicates the binding energy of that metal, binding energy of the electron to that metal. The question asks the number of metals, find out the number of metals which will show photoelectric effect when light of 300 nanometer wavelength falls on the metal. So, I am supplying energy where corresponding to lambda equals 300 nanometer, and I know that this energy. So, there was this conservation of energy from the photoelectric effect discussion. This is the energy of the radiation, this corresponds to the binding energy or the work function phi, and the remaining part of the energy will be used for the kinetic energy of the electron. So, unless the energy of the radiation is more greater than phi, there will be no photoelectric effect. So, the question essentially asks us, if lambda is 300 nanometer, what is E? If you calculate E in terms of lambda from this expression, you will get the energy as 4.13 electron volt, and you see if the energy supplied is 4.13 volt, lithium requires only 2.4 electron volt energy. So, if I supply this energy, lithium will be happy to give me that electron. Similarly, sodium is all right, potassium is fine, magnesium is fine. When I look at copper, it has got 4.8 electron volt, and I have got only 4.13 electron volt from this radiation. So, from the photon. So, this cannot remove photoelectron. 4.3 greater than 4.13, it cannot. 4.7 again cannot. 6.3 is way high, cannot. 4.75 it cannot. The question is find out the number of metals which will show. So, I can see 1, 2, 3, 4, only 4 number of metals that can show, that will show photoelectric effect when I supply this radiation. Let us look at the next question. This concerns the de Broglie hypothesis. It tells that the atomic masses of helium and neon are given 4 and 20 AMU. The value of the de Broglie wavelength of helium gas, which is at minus 73 degrees Celsius, is m times that of the de Broglie wavelength of neon gas at 727 degrees Celsius. What is the value of m? Neon gas is kept at temperature. So, let us find out the temperature of neon gas, 727 degrees Celsius, which is 1000 Kelvin. Temperature of helium gas is minus 73 degrees Celsius, which is 200 Kelvin, all right. And it says find out the masses are given, it find out the de Broglie wavelength. What do we know about the de Broglie wavelength? As we know that de Broglie suggested that for a particle with mass m moving its speed v has the de Broglie wavelength of lambda, which is given by h by mv or h by momentum p. The question says that these two gases are kept at different temperature. So, let us see, so that if I say the question tells how many times helium has. So, it wants us to determine lambda He divided by lambda Ne. This is what we wanted to get. If I use this equation, H is a constant. So, I can write lambda He divided by lambda neon is the momentum of neon divided by the linear momentum of helium. So, this we have to determine. And what do I know about the what does the question tell us, give us to know about the momentum? See, this tells us about the temperature. We know both helium and neon are monoatomic inert gases. So, their kinetic energy. So, if this is the temperature, the kinetic energy of monoatomic gases is given by 3 by 2 kT, and where T is the temperature, all right. And we know that kinetic energy E is p square by 2 m, the square of momentum divided by 2 m. So, therefore, momentum is 2 m kinetic energy square root, all right. So, the momentum of Ne divided momentum of helium, which is what we are trying to get, is therefore 2 mass of neon, kinetic energy of neon, and what is that, which is 3 by 2 K, this is Boltzmann constant, and T is 1000 Kelvin for neon. I am not writing down the units, because both will have same units, they will anyway cancel. So, 2 mass of helium multiplied by 3 by 2 K and Boltzmann constant, and the temperature is 200. They are all multiplied, and this is under square root. And mass of neon is 20 AMU, mass of hydrogen helium is 4. So, this is 20 divided by 4, 2 and 3 by 2 and K 3 by 2 K cancel. So, I have 20 divided by 4 from mass, and then 1000 divided by 200, which is 5, and this is 5 into 5, 25, square root of that is 5. So, the final answer m that we need is 5. These are the few questions that I could find from last few years of joint entrance JEE questions that are related to the subjects that we discussed. During the course of this lecture, I collected some material from the books that are listed here. If you have any questions or queries or comments, you can always write me at the email address that is being shown here. I hope you enjoyed the course as much as I did delivering it. Thank you very much.